All right, so last lecture of the semester, and we only have so much time. I still have streams and groundwater that I'd like to cover, and I find myself in this situation quite frequently. So what I've got, and I've made over the years, is a sort of hybrid, slimmed-down version that I'm going to use today, and I may even delete a slide or two as we're talking. I made a fresh save on this, gave it a new title. In case I actually do end up deleting stuff, I'll have my new abridged version. The problem is, if you couldn't tell, I often talk ahead of my slides, or sometimes even nowhere near my slides. And so I have a talk about streams, I have a talk about groundwater, and the problem I have is then sticking to said abridged slides. So I will do my best, but we may find ourselves once or thrice in that position where I'm talking about something that I've already deleted. So bear with me. I will put this new version up, whatever it ends up being, so you guys have the access to the handout. So this picks up, as it says, part 2 of Water Everywhere. What was Water Everywhere? That was the hydrologic cycle lecture, the groundwater lecture, not groundwater, the water cycle lecture, all right, that we had however long ago that was. Where that left off was that water does one of two things when it falls to the surface. It stays at the surface as runoff, or it percolates into the ground and goes into the groundwater. So we're going to attempt to finish up that conversation in this conversation. So runoff, as we indicated before, that's what we call surface water, and that is streams and lakes. Okay? When we talk about percolating or infiltrating down into the water, different texts use different terms. They mean the same thing. Trickle. You could also say just good old-fashioned trickle into the ground. That's obviously it makes groundwater. Coming off of a semester where they make up complicated words for stuff that, we should be happy that we've got nice words like surface water and groundwater. You know where those things are. Okay? Anyhow, we call those aquifers. So we still made up a complicated word, but that one at least is sort of in the common conversation, common language. So we're going to start by talking about surface water or streams. And one of the first things we need to do is get across the idea that you may have a river by your house, or a stream, or a creek, or a crick, or a brook, or there's probably half a dozen more words that are escaping my mind at the moment. Those all sort of imply size, if you think about it. All right? In earth science and geology, we just use one term. I don't know why they picked which one they picked, but they did. They used the word stream. All right? We first encounter this problem with some folks when we're doing topo maps, and I ask them to find a stream on the map and measure it, remember, and then decide the gradient, and you're like, there's nothing on here called stream. We've got Sequoia Creek. Can I use that? We've got the Mohawk River. Can I use? Yes. Sorry, geology thing. All right. So they're all called streams when we're talking about them, because we don't really care in this context at any rate how long they are, how wide they are. We do, as you'll see, have an equation about that eventually. But, yeah. So everything's a stream. And, it's got a couple caveats. The canal is not a stream. It's man-made. And, yeah, arguably, maybe there's a wee bit of flow. This picture's a little hard to see. But I purposely chose this one because you could quite easily just be standing there and taking a picture of the rocks at your feet. Right? It's hard to tell scale, but if you look enough, you'll see way down there on one of those rocks is a cow and some guy about ready to try and walk through the creek there. So, size doesn't matter. We don't care. Divides. Watersheds. Possibly a more popular term. Drainage divides break up the watersheds. Somewhere on my phone and or my wife's phone, there's two signs, I think. And it's coming back. It's before Albany. I'm sorry, it's after Albany. You're coming back from Massachusetts, anywhere there on 90, I believe it is. And it says this is the highest point on Route 90 until you get to such and such, South Dakota, which is mind-boggling, really, if you think about it. It's a long way away. But they don't call it the Great Plains for nothing, right? And, you know, Midwest is pretty flat. Trust me on that one. But you just, when you see that, kind of catches you off guard. So there's a good reason there's a sign for it there. Well, right around there, there's also another sign that I have slightly less pictures of that I never managed to get into my PowerPoint that says, you hit the different watershed. That's what these divides are. They're high points. All the water to one side flows into one watershed. All the water to another side flows into another. Kind of like your roof. You stand on the sidewalk watching it rain, and all the rain that comes to the right side of the peak flows, guess what? To the right side. All the water that flows just to the left side flows to the left side. Makes perfect sense there. Well, the same thing happens on the surface of the earth. So we've got a handful of divides. You may have heard of the Continental Divide. All right. That's a famous one, so to speak. The rest of these, I don't know. I think it's really only famous because it's, the Rocky Mountains. Hikers like to go there. But we've got some other ones. The one that always surprises me is the one there just south of the Great Lakes. You really wouldn't think of that as a ridge line there, let alone the one that moves up into Canada. But it doesn't take a whole lot. It doesn't take a whole lot to get higher there. But the Continental Divide, that's very, very obvious. And the Appalachians, to some extent, work in the same way. And there's another little one over there, the Great Basin. The geography, the topography is such that everything, that falls around that one area, look way north of California, well, not way north of California there, you'll see the Great Basin. So, yeah. And then those funnel water into streams, smaller streams that feed into medium streams that feed into larger streams. And if this were your geography class, I don't know if they still make everyone learn all the rivers and everything, but you could probably pick out a handful of those rivers on there and say, oh yeah, I know that's this, that's that. So it's all just part of, drainage systems, rain gutters. Just another way of looking at it. We don't need to spend too much time on it. I don't use the word drainage divide. No. Too much. All right. I know we're just coming off of glaciers this semester. We had way more vocabulary words than you guys want. The next lecture test is going to be chock full of vocabulary words. We got to throw some more at you. All right. We got... going to start up at the top of this hill here, and again, scale is iffy. We could easily be, a couple thousand feet up and 10, 20 miles long in this picture. So at the very top of the stream system here, we've got the headwaters. Headwaters are where the stream starts. Okay, in this one, we've got a multiple. And And this is what confuses a lot of people. You zoom down to local map level. Each one of those little branches there, locally, colloquially, might have its own name, okay? And sometimes they show up on the map, sometimes they don't, depends again on your scale, so on and so forth. There's a zoom in slide or two later, if I kept it in this abridged version here, that'll show you that, you know, any one of those little branches up there at the headwater has, you know, like veins on a leaf on a tree, 2-3 dozen little streamlets coming into it. Okay, so you can only show so much. Anyhow, so headwaters are where a stream starts. They're up at the top of the basin. All right. They eventually come together to, well, let's hit tributary first. So the next word is tributary. All right. Tributaries contribute water to a stream. Tributaries feed a stream. All right. So all those little streams coming in, the headwaters up at the top there, all right, those are technically tributaries. They wanted to separate it out for educational purposes here, and we left those as headwaters, and then some of the feeders lower down, they're calling tributaries. Not a big distinction there. Anyhow, all of those come together to form the main stream system called the trunk. Okay. Around here, you would argue that the Mohawk is the trunk stream, and everything feeds into that in some way, shape, or form. Hudson's another great, even greater example of a trunk stream. And again, it's a function of scale. Something that might be a trunk stream over here could feed into, you know, like out in the Midwest where I came from, everything supposedly, more or less, fed into the Mississippi from a certain side. So the Ohio River was a major stream system, but it fed into something bigger. So it's all kind of relative. But anywho, so the trunk is the main part of the stream. I want to add a word that's not on here. It's a distributary. All right. And guess what? Like a tributary contributed water, a distributary distributes water. It takes water out of the system. These, I don't want to say they aren't as common, but they're a little harder to get. And again, they have to be a function of topography. You got to have part of the stream branches off and goes down a hill, you know, and over time it becomes bigger and bigger and bigger, carves a little groove for itself. So tributaries and distributaries. All right, so we're coming down the hill, and we've hit the floodplain. We'll get to defining floodplain a little later. I'm sure you got a pretty good idea what goes on there. And things level out, and the stream slows down. Once the stream levels out and slows down, it starts to do something called meandering. Again, a word you've heard. The little old man meanders as he's wandering around. A toddler meanders, perhaps, as they're wandering around. Well, streams do that as well. And again, I'm not sure today how far we're going to get into meandering. But basically what happens is, you know, the little bends that are naturally there, very few things are super, super straight in nature. All right. As the stream bends, again, over time, because of differential weathering and erosion, those get accentuated. And they make bigger and bigger bends, and you see those snaky curves in there. Okay. Then, as we wander down even closer to where the stream lets out, in this case, we're at some standing body of water. We're going to call it an ocean just for conversation's sake. We've got the mouth of the stream. So haven't traveled really that far. You got the headwaters, you got the head, and you go as far as the mouth. Could add the tail of the stream, maybe the stream anus, but you know nobody wants to live near that. So it is what it is. The mouth of the stream, it spews forth, comes out. I guess that's the reason they called it that. All right. Now, while you're at the mouth of the stream, at a standing body of water, something tends to form. It's called a delta. You've again probably heard of delta in your Western Civ class. Maybe if you dig blues music, you've heard of delta blues. There's Nile Delta, 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 Delta. It's all over the place. It is, of course, named after that triangular-shaped letter. And that is more or less implied with all the little streamlets here down at the bottom where that number 5 is and the word delta is. But you can't see that in the back of the room probably. So those are kind of cool. They're a depositional feature of a stream. They always talk about streams transporting sediment. All right, we've got a dredge stream so we can get our big boats through and all that stuff. Sediment, sediment, sediment. Well, all that sediment that the streams are carrying stops at some point and gets deposited. Remember, that's the end of erosion, is deposition. So that's at a delta. Now, what happens is one of those, half dozen, however many streamlets are down there, okay, was the original one. If you recall way back to our conversation, the velocity of an agent is usually what's responsible for erosion, what size sediment can be carried, so on and so forth. So again, we came down into the stream valley here, into the floodplains. We're slowing down. Gradually, smaller and smaller sediment is being dropped. First the largest stuff, then the medium stuff, okay, so on and so forth. That stuff's all falling out. So finally, by the time you get to the end of the stream, you only have your finest grains left, and they hit that water. Now you're thinking, okay, he said ocean. Ocean's always moving. You got the waves. Well, compared to that stream, those waves are like hitting a brick wall, okay? And even if it's just a big lake, same idea. And that sediment immediately falls out of suspension, out of the water, and gets deposited. Now we're talking hundreds, thousands of years here. It blocks itself up. Just like we have to dredge the stream channels for the boats, okay? There's nobody here to dredge this. It blocks itself up, it backs up, finds a new little channel, carves through there. There's a low spot at first, it turns it into a channel, and it does that for another couple 100,000 years, whatever. That blocks up, moves over a notch. You know those sprinklers you see like they always have on golf course? They go and then come back. All right. This is a very, very slow version of one of those. Thousands of years just moving across. And that's what makes that fan shape, that delta deposit. We like them, historically speaking, because think of all the gunk, okay, that's been in that stream. You got rid of all the big rocks already. You got sand, silts, clays, mostly silts and clays, which aren't the best to farm on, but there's so much nutrients that came down that stream as well. Think of all the dead things and poo and everything that got into the river along the way. All that comes down, all that comes out. Those deltas, that's why they're so fertile. All right. So, anywho, delta. We'll talk more about floodplain a little later, but just in case we don't, what do you guys think happens on a floodplain? It floods, yeah. Guess what happens to people who build houses on floodplains? They flood. And yes, the insurance is a huge thing, and huger than you may only half-jokingly guess there. I was still in school, so somewhere around the mid-90s-ish, Mississippi did her thing again. And I'm going to say hundreds of millions. It was probably in the billions of dollars. Just claims came in. And the insurance companies finally said, no, we can't do this anymore. And there was a huge change in flood insurance. I don't know the details, but they basically just said what I said. Look, you're living on a freaking floodplain. It's a beautiful view. We get it, but you can't cry when your house floods. You're on a floodplain. And you want flood insurance, fine, we'll sell it to you, but it's going to be, a hell of a lot more, They made major changes to it. We moved in to Utica, like I said, 22 years ago. We were not even 100 yards off of Sequoia Creek. I said, I want flood insurance. They're like, no, you can't get flood insurance. You're fine. You're fine. And I'm like, I don't think so. So I went and got myself a FEMA map. And they're like, oh, where'd you get that? I'm like, FEMA. And I was in the just outside of the 100 years. Like, I still don't believe this. It was an old map, too. So it took us until 2018 till we finally flooded. It stayed fairly true to FEMA's maps. It came up like 2 houses away from us. 1 house even. The neighbor came over. And there might even be a picture in here later. I don't know if I kept it in. And the police were on our street. They had the barricades up and all that crap. And he's out front talking. I'm like, Rex, you leaving? Hell no. Okay. We're not going anywhere either then. And he went up to his driveway and went back down 6-8 hours later. But boy, it was nerve-wracking. After that, like I said, 2018, it flooded 4 houses past us. And then they're like, oh, yeah, well, a few years ago they started selling flood insurance. I'm like, yeah, okay. We didn't have flood insurance. But things changed. Why did things change? Because we paved. Anywho, enough about that side rant. So floodplains, you're going to flood. You can't bitch and moan like I just did when your house floods. So they're flat, they're plains, because all that sediment up and washes out and over the sides. Okay? Again, we talk about streams carry sediment flowing along. You're going to be shown an equation. I don't know how much we're going to screw around with it today. Q equals VA. It explains flow rate. And basically it's dependent on the channel, the speed, the channel size, the speed of the water, and the quantity of the water. And a flood messes with all those. The one in this conversation right now is, what is a flood? A flood is when the water goes over the stream channel, right? That's increasing the size of the channel. It drops the velocity like crazy. So what happens then in these plains is the water comes over the side, all that sediment falls out, goes into all the nooks and crannies that were there before, any little variances in topography get filled in, and you end up with these nice flat, football field looking things. So you don't always have them on both sides of the stream. Sometimes it's just one. Again, sometimes, mountains get in the way, hills get in the way. If you've ever gone down to Starch Factory Creek and screwed around down there, you've got a big ridge line that leads up to Masonic Center over there, okay, which just, prohibited flooding from going in that direction. So all the floodplain is on the other side. We've got all those awesome 1930s buildings over there. So, all right, so floodplain. So we've got, again, just to round this up before we get off this slide, we've got headwaters, tributary, distributary, trunk, delta, mouth, floodplain, and I forget if I said meander or not. It's a lot of vocab. Now, this is not a labeling diagram on the test. It is vocabulary words, but they're pretty straightforward. A tributary does what? A distributary does what? The mouth is where. The headwaters are where. Okay? Pretty simple stuff, but you'd feel like a fool if you missed it too. So give it 5 minutes of review. There's all the important words. I think we hit all those. Oh, the channel itself. That's the ditch, okay? Stream channel. I use that word actually a couple times. Pardon the wonderful drawing here. Coming off of my glacier diagrams, this is even poorer. So this is me attempting to draw a stream channel. Okay? And what we're looking at first and foremost is the U-shaped part in the middle there. And we want to clarify really, 2 terms. Bank as in stream bank, and bed as in stream bed. The bed is the bottom, BB. All right, stream bed, that's what you are probably walking in. If you're ankle deep, trying not to slip on stones, looking for crayfish, whatever you're doing, that's the stream bed. The banks, I don't want to say they aren't always there, but they are not always there, at least more than a couple inches. The banks are technically the sides, as in vertical. The problem is a lot of you say, yeah, I'm sitting on the stream bank, standing on the stream bank, where you're fishing, where your lawn chair is, where your beers are, whatever. Okay? That is the floodplain, really, because it's up and flat off the side. The bank would be that 3 inches that you got to step down. It's not always as dramatic as I made it in here. Now, don't go correcting your grandpas or your uncles or whoever takes you fishing and so on and so forth. But now you know. When you got kids, you can say, a lot of people will say you're sitting on the stream bank here, and they'll be rolling their eyeballs just like we did at our adults, right? But we're on the floodplain. You see here, that couple inches down, that's the bank. But a big deep river, all right, which is what we're drawing here, at some point that bed curves up. Once it starts curving up and going vertical, that's when you've hit the banks. So, pain in the butt technicality, but that's what scientists are all about, right? All right, so come up and over the side, you got your floodplains. Now I drew these little shoulder pad looking things there. What the heck are those? Those are levees. Again, we've heard of levees. You drive your Chevy to the levee's going to break. There's a handful of other things we know about levees. All right. What a lot of times we don't know is that they are natural in many cases. Now, those big cement things you've seen, those aren't the natural ones. That's us coming along and augmenting them because we tend to, as we noticed, build right next to streams. 100 years ago, there was great reason, right? Transportation. And even as far as putting train tracks on floodplains. Why? Well, it's flat. It's really easy to work on. And again, you want your train close to your boat and vice versa, whether stuff's coming off the train onto the boat, off the boat onto the train. 100 years ago, made sense. You put up the occasional flood. Again, there was a hell of a lot less pavement back then. Arguably wasn't as frequent. Another conversation. Anywho, nowadays, happens more. So levees, again, we told you that water comes up and fills the floodplains in, all the nooks and crannies. Well, what falls out first, the littlest stuff or the biggest stuff when that velocity drops? Okay, it's been a while. You might not remember. The biggest stuff drops first. Just like you trying to make one trip from your car to the house with all your groceries, and you got a bag hanging off of one pinky, and you got a gallon of milk hanging off the other one. Which one's going to fall first? Whichever's heavier. Okay, usually the gallon of milk, but you never know. So what happens with these levees is the bigger particles fall out first, and they build up this ridge. All a levee is a ridge of sediment along a stream. And what it actually does is it extends the banks, it increases the channel size. The stream's not thinking about it, but what it's doing is it's deepening its channel, it's enlarging its channel, making it less likely to flood. It's really not in a stream's best interest to flood. Again, it has no thoughts about this, at least as far as we know, but that is inevitably what it's doing. So levees are natural flood deposits, okay, right as we leave the stream channel and entering the stream levee. The ridges along the sides of the stream, so on and so forth, everything else I said. And we, as I also said, often go along and enhance those, pour cement on them, all kinds of wonderful things. But it is necessary because how many times are you going to see, the downtown area right on the other side of that street? Think about all the small towns you've driven through over the years and so on and so forth. So here's that conversation we just had about levee formation. This is not exactly Noah's flood here, but this is one hell of a flood for this little stream valley. All right. A is a normal day. B is pretty catastrophic flood event for that area. And you see that the sediment came up and got deposited on either side of the channels. As it goes back down, then you're left with these things. And I drew them, of course, very humpy looking. They are going to have more natural form to them, kind of like they're drawn here. black swamp. You don't need to worry about that, but I'm sure you can envision it. Again, it's a function of topography. In this case, you got that ridge so close to the levee. It's going to be really marshy and sticky back there certain times of the year. Okay, we're keeping oxbow in here. No, I'm going to drop oxbow because, yeah, we're going to skip. So, skipping oxbow. You could write skipping meander and oxbow. I already told you a couple minutes ago when we talked that natural bends or streams, natural bends in the stream get augmented over time. There's a 5-minute conversation on how that happens. It involves marching band and auto racing. We'll do that on another day. All right, real quick. So if you're on the outside of the track, what do you got to do to keep up with the guy on the inside of the track? You got to go faster, all right? Same thing on marching band. Let's say you guys are making a big turn. Person at the focus point of that turn more or less stays in place. I usually ask who's in marching band and who likes cars, but there's only 3 of you today, so we're not going to play that game. The guy all the way out on the end, they got to like triple step to keep up with the guy that's standing still because they're making this big bend. All right? You're told that because the band instructor is telling you to do that. The car driver knows that. The horse rider knows that because they know that. Okay? A track is 2 circles. One on the inside, one on the outside. Stream isn't thinking. But the same exact thing happens because water molecules stick together. Remember that polarity conversation from so long ago? That's essentially a marching band line full of water. So when it goes around a curve, the outside of that line of water moves faster than the inside of the line of water. Put back into place what we know about weathering and erosion and the agents we just talked about. It's velocity-based, right? So the outside is going faster. That's going to dig out or eat out more so than the inside. The inside is oftentimes so slow it actually gets deposition. So what that does is it actually moves that turn, as we see through the pictures here. It moves that turn towards the outside of the bend. So this top one here is an outside. This top one here is the outside as you're going around that corner. So what we see here is those outsides coming together. Eventually the stream just hops the channel, carves another groove, cuts off the old meander. We're now talking about this, so it's back in the test. The old meander is now called an oxbow. You're thinking, what the heck's an oxbow? This is a very old term. You might know it as a yoke. Right, what we put over our horses so we could plow. You all did that this morning before you came to class, right? Mm-hmm. So, you've seen one on TV, though. All right, it's that big, curved, omega-looking, horseshoe-shaped looking piece of wood or whatever they put over the oxen, between the head and the shoulders, I guess. That's what an oxbow is, and this there reminded them of that. You'll see these out when you're walking. You're not going to recognize it as such. You're going to say, wow, this is a really short stream. They're really obvious, and I took that picture out. They're really obvious from the air. So differential weathering and erosion. This also tells you exactly where you're going to see gravel bars in the stream. Again, if you've poked around Starch Factory Creek, it's got its gravel bars in all the right places. Tells you where stream velocity is going to be higher, lower, all kinds of neat things. Meandering increases with age. The longer a stream's flowing, the more it meanders. Like I said, just like a little old man. We've talked about this several times. Don't forget it. Almost done with streams. So, a lot going on here. What we want to focus on are 3 of those words, plus one I'm going to tack on at the end. Dissolved load, suspended load, and bed load. Dissolved load is just that. You don't think about it as erosion, though. Say you've got well water, a friend of yours, family of yours has well water, and It's sulfury. It's eggy water, as we say. All right? Or somebody else you know has hard water. They have a water softener. Hard water is calcite in the water. Or what's the other one you see all the time? Iron, right? You get iron deposits sometimes in your sinks and your toilets. All that stuff is dissolved into the water. In order to be dissolved into the water, it had to, well, dissolve at some point A. In order to be deposited in your sink or your toilet, it had to be dissolved at point A and transferred to point B, which is your sink or toilet or your cup of water or whatever we're talking about in this conversation. That's erosion. It's movement, transportation of sediment. It happens to be dissolved, though. So that's what dissolved load is. You don't really see it. It's there. A handful of things dissolve very easily into water. Suspended load. Suspended load is, again, just that. It's stuff floating around in the water column. That classic experiment that no one I've ever talked to has done, but they always talk about it, like teachers can run out and grab a cup full of stream water and set it on the counter. What do? Well, you go down and you see the stream's all muddy, especially after a big rain, right? You know, hey, my stream isn't usually brown. Well, it is today. So you go out, you get a big cup full of that water, you set it on your counter, and after an hour or two, what do you got? You got clear water with a 1/4 inch of sediment on the bottom, right? Turbulence keeps that stuff suspended in there. Tiny little particles, silts and clays, floating around. That's why it looks all muddy, but it's the motion, though, that keeps that stuff suspended. So dissolved load, as we see here, is silts and clays. The part's actually important. Because I'm not going to ask you what dissolved load is. I'm going to ask you what sediment size can be dissolved load. Lastly, we've got bed load. Bed load is the stuff that is too heavy, too large. So sand, sand, pebble, cobble, that kind of stuff. Bed load is stuff that's too heavy to be picked up and carried. So it rolls along the bottom, banging and bouncing into other stuff. Remember the word abrasion? We talked about that again when we did weathering and erosion. We're really still talking about weathering and erosion, if you haven't noticed. There is one term that's not on here for some strange reason. Let's see if it's the next one. Yeah, it's not even the next one. Saltation. Salt with ation on the end of it. All right. Saltation is a hybrid-y kind of thing that applies only to sand grains. And there's a picture of saltation here. This is this little guy towards the end. Looks like he's bouncing, rolling down a hill and bouncing. And that is the water is almost fast enough to carry it. Picks it up. It's like, oh, I'm going to carry this sand grain. No, I'm not. And sets it back down. Like, all right, let's try again. Picks it up. So the velocity is right on there, and it happens enough, apparently, that they gave it a vocabulary word. Okay, saltation. Saltation has nothing to do with salt. I guarantee you there'll be one answer that does, though. All right, but saltation refers to sand-sized grains moving along in a stream column. All right, and it is, again, it's a function of velocity. It's not quite fast enough to carry sand, but it really wants to try. Now, again, what do you got to do to carry sand? What do you got to do to carry pebbles? Just jack up that velocity. We're definitely not going to talk about floods and what happens during them today, but think about it. You see stuff going down a stream that normally does not go down a stream. You see sediment deposits all over the place when that stream goes up and over its banks. And normally that stream isn't carrying. That faster water carries more bigger stuff, okay? So on a normal day, a typical day for this stream, it could barely carry sand, and they, again, have a word for that called saltation. Let me see what I got left here. All right, let's just finish this puppy. Stream flow, flow rate. You guys all did the flooding lab this semester. This seems apropos, I suppose. I had a couple questions at the end of the flood lab that asked you about various flows that you graphed. You probably didn't look at seasons, but you might think that your heaviest flows we're going to be in early spring, late winter, early spring. A lot of times that's absolutely correct because of snow melt, especially around here in a typical year. However, some downpours, not related to snow melt, can also seriously jack up the amount of water in a stream. Again, the more and more we pave, the more and more that becomes an issue. So precipitation and snowmelt are the two biggest factors of what controls the amount of water in a stream. That's only part of the equation, though. The other part of the equation is gradient, slope. Gradient is sort of the opposite of slope. But, so, how big is that hill that it's going down? And just like as you figure out as a toddler with your Matchbox car or your Tonka truck or whatever, the steeper that little slope you've got it going down, the faster it's going to roll across the floor, the farther it's going to roll across the floor. We figure out physics fairly early in life. Streams are doing the same thing. Now, what you might not know is that increasing that water volume also will increase the rate, not just making the slope steeper. That one was common sense. The other one, maybe not so much. We've got a formula. We've done very well at avoiding math in this class. Got a little bit right now. It's not bad, I promise you. Q equals VA. Q is discharge, V is velocity, A is area. Back when I first started teaching this, I had an entire semester on hydrology, which is water flow. And I had this class, and I had classes in between. Somehow, Q equals VA more or less eluded me until I started teaching. And I was grumbling. I had a colleague at the time, and I was grumbling to them about, what the hell is Q for discharge? Why don't we use D? This makes no sense. Why Q? Why? I must have been really grumbling. He's like, quantity? Oh, of course. And the quantity of water in a stream, for reading this equation, which I recommend for any class that you have equations in. I wish, again, I had known this when I was in school. Read an equation like a sentence. Translate those variables into words and read that word as a sentence. If you have trouble with equations, which I did, mainly I didn't take enough time to learn them probably, but nonetheless, translate it and make a sentence out of it. The quantity of the water in a stream is equal to the velocity of the water and the area of the channel. Well, that makes actually a good bit more sense. Area of the channel especially, the bigger channel is going to allow you to have more water in it, right, than a smaller channel. And when you learn how this is actually measured, the velocity makes perfect sense because we're talking about gallons per minute, cubic feet per second, flow rate kind of stuff, okay? So velocity then, the faster that water's flowing, the more water you're going to be able to get through. So bigger channel's important, bigger pipe, think of it as a pipe flowing. And you're sitting there counting the water molecules that go by, or the gallon-sized jugs of water that are floating by you to think about gallons per minute. A faster stream is going to get more of those jugs of water by you than a slower stream would. So velocity is important. So discharge, quantity of water flowing through a point in the stream for an amount of time. We talk about flow rate, we talk about gallons per minute, we talk about cubic feet per second. All right? All right. So, again, we have all this. We're going to calculate the discharge of a stream. Now, I told you that the math isn't hard, it isn't scary. I am never, ever, ever going to give you numbers. Some of you don't even need numbers to work this out because you can sort of logic it out. But if you need numbers to help you answer the question, make it simple. Q equals VA, 25 equals 5 times 5. You could say 100 equals 10 times 10. I don't care what you use. Start with something that you know to be true. 4 equals 2 times 2. I don't care. Some people see an equation and they're like, I can't do equations, and they just shut off. You can do equations. If you can do algebra, something times something equals something, that's as good as you need right now. We got to divide in a minute, but still, you could do that, especially if you know starting numbers you know. Okay, so what are we doing? I'm going to ask you, what would happen to the stream if the velocity stays the same, but the channel size decreases? So you're going to say, okay, we're going to keep 25 the same because he didn't say anything about the quantity of water. He asked me about velocity, so we're going to turn that 5 into a V. And he said that A has to go down, so let's make A a 3 in this case. Now, you may not know off the top of your head what 25 divided by 3 is, but you got a pretty good idea that that means V has to be higher than it was, right? Because 5 times 5 is 25. Now, 3 times what is 25? It's got to be a bigger number than 5. You know that V has to go up. Let's say I'm going to ask you what happens to the velocity of the stream if the channel size increases. Well, then you make 5 a bigger number. Make 5 7. What's 25 divided by 7? Who knows, but you know it's smaller than 5 times 5. Has to be, mathematically speaking. So you know that that velocity is going to decrease. Now, like I said, some of you already know that simple relationship. If A goes up, V has to go down. If V goes up, A has to go down. You know they're connected. Some don't, though, so that's fine. I'm talking to those people right now. All right? You can put in numbers if you need them. I'm never going to give you numbers. Trying to help you by not giving you numbers. This is very easily observed. Again, homework for you this spring, this summer. You're walking along a stream. Pay attention to how fast it's flowing and how wide the channel is. You're walking somewhere that it's nice and wide. You're walking along with your lover and just holding hands and enjoying the nice day. Stream's kind of trickling by, and then all of a sudden you notice it's really loud, and you're like, oh, it sounds like the water's flowing faster. Look over and see if it's narrower. It probably is. Or if you've been along a loud stream the entire time, and all of a sudden you don't notice the flow anymore. Oh, I don't hear the stream anymore. Look over there. It's probably wider. It's perfect. Since it happens in nature all the time, we just explain it with math. Okay? So that's varying area. The flood situation, which of those letters is the flood most directly? Is it the quantity of water? Is it the velocity of the water? Is it the area of the channel? Arguably, it's all of them, but most directly, what is flooding? Yeah, Q. It's a heck of a lot more water. That's why the whole problem is happening, whether you had a whole lot of rain or whatever. So what we tend to ask if it's a flooding scenario is, what happens if you increase Q? What happens to V if you increase Q while A stays the same? And of course, if you're increasing Q and A, V's got to go up too. Okay, so in a flood, water flows faster. Now, here's where it gets weird. We don't technically call it a flood unless it's gone over the banks, right? We wouldn't call it a flood. We just say, damn, the stream's flowing fast today. What letter is that changing when you go over the banks? A. That's area. So the minute you go up and over those banks, your A just changed dramatically. So we'll remember we were talking about levees and floodplains? If A all of a sudden doubles in size, Q is arguably the same for a moment, what happens to V? Plummets. Your sediment goes whoosh and drops. I hate it too when math solves everything. Okay, I get it. But in this case, and it's even simple math. Now, the only way that this works, unless you want to go up into differential equations and all that fun stuff, you got to think of this as Polaroid moments. You guys are a little old, but I think, or a little young, but I think Matrix is still kind of out there in the common world. Okay, the movie. And those little stop action sequences that were so popular and huge back then. You got to look at this stream in that way, or you can't do the math. Because there is that moment where Q increases to such a point that A, all of a sudden, boom, goes over the sides. And V drops. That is one snapshot. A second later, it's completely different. Mother Nature doesn't have to do math. She doesn't need to worry about that. She just does it. Math is our attempts at explaining it. But when you string all those little moments together, you can do the math. So, anywho, you're just going to see one, maybe two questions about it. Don't freak. And like I said, probably you'll see, it's either going to be the area question, area of the channel, or the flood. You can manipulate this artificially any way you want, but those are two real examples. All right. I got 20 minutes to cover groundwater. I can do that. Especially by pausing for 30 seconds and staring at the screen. That helps. I love these wells they always put in here. When's the last time you saw a stone well with a bucket and a handle on it? Yeah. So they boarded them all up because children, evil children, kept crawling out of them, but and falling down into them. Poor innocent children, and they come out evil children after this. Anyhow, that movie forever traumatized me. Was it The Ring, I think? Oh, okay. Horrible, horrible movie. Almost as bad as that I See Dead People one. That really freaked me out too. Yeah, did the little girl crawl out on the TV and everything? Oh, that was messed up. Yeah. Messed up. Hate wells. All right, so anyhow, so they boarded up all the wells on the planet after that came out. But you've seen these, all right? Hansel and Gretel going up the hill. No, that's wrong kids. Jack and Jill going up the hill to get the pail of water. So, really, they should have got the water at the bottom of the hill, but whatever. They're probably trying to avoid pollution. You get to the top of the hill, there's less pollution up there, maybe. So we got a couple things going on here. We want to talk about the saturated zone first and foremost, that blue area down at the bottom. Then we got the water table. We're going to ignore capillary fringe. Capillary fringe is what good paper towel does. Bounty. You put Bounty next to a puddle, what does it do? It slurps it in. Okay? Don't need to worry about that. Vadose zone, I'm changing the word for you again to something simple. We're going to call that the unsaturated zone. We got the saturated zone and the unsaturated zone. What happens in them? Guess what? Saturated zone is full of water. The unsaturated zone, not so full of water. That's what we're illustrating over to the left here with these little enlargement cubes of 3D-ness. The one on the bottom you see is all blue and brown. The one up at the top is blue, brown, and white. That white is supposed to indicate air or gas. I try really hard to say gases. I always say air like this does. We should say gases. If you've had any environmental science, you know that like bacteria in the soil and in the ground can throw, like nitrogen's a big one. They can make all kind of extra nitrogen. All right, so this isn't necessarily our air that's tied up in this soil or in these rocks. But keep it simple. They say air. Anywho, so saturated means all of the pore space. Remember pore space? We talked about it a little bit when we were making sedimentary rocks. The fact that all the little pieces, parts are different sizes and shapes, and they don't go together. And even if they were perfect spheres, think about the last time you set up a rack of balls to play pool. As tight as you make that rack, you've always got the holes in there because you can't get round balls to 90-degree angles. Not happen. So no matter what you do, you inevitably, invariably have some pore space. That's where the water goes. It's really hard to imagine that piece of sandstone we had in lab, that water can flow through there, but it does. It can. at any rate. Limestone as well. Sedimentary in general. Igneous, not so good. Metamorphic, not so good. Typically when we're talking about groundwater, we're talking about sedimentary. So anyhow, saturated zone, all that pore space is filled with water. Unsaturated zone, it's a mixture of water and air. Gabish, we good? What divides the two? Something called the water table. You've heard about it before. Is that a fixed line or does it move? All of you. It moves. Yeah. Why does it move? Well, usage, rain, lack of rain. When we first moved here, Nirvana opened up their plant, not the band, but the water company, opened up their plant up north, wherever the hell it is. And it's not Nirvana anymore, it's another company, but they're still up there pumping water. And it made the news, not because Nirvana was coming to town, but because everybody's well dropped, which makes perfect sense. What was there before? It wasn't another water factory. It was a sheep farm, if I remember correctly. And because I always say, Nirvana, sheep. I did like Nirvana water. It tasted good. Probably the sheep. But at any rate, so they start pumping out all this water. Sheep poop. Yeah. Anywho, sheep farm turned water farm, and everybody's water table dropped. Go figure. All right? So this is a variable thing. You guys right now are not getting wells drilled. In the future, 10 years from now, maybe you're buying some land, not in a city or a suburb, but out there, and you might find yourself in a position to get a well dug. Well records are public record. They're open. Everyone can see them. Don't hire the cheapest guy like I always do, okay? Or if you do, make dang sure you know where everybody else's well is. Because as you're going to see, there can be false water tables. Or they could be doing it, in March, April, where there's all the melt, the rain, and that water table might be higher. They say, okay, you're good. And then come June, you're sucking air. Yeah.
So, would the best time be when you have a burn ban?
Arguably, in low water situations, drought situations, I'm overemphasizing the point about it. It can drop significantly. Does it typically? There's a lot of factors. The best thing to do is honest to gosh, look and see what your neighbors are. If they're all at 1,200 feet, don't have your guy cut $500 off the bill if he stops at 800 feet. Probably not a good idea. And if anyone who's honest about it, should do that. That's kind of a really specialized field. We're still marred because when we first moved here, I think I've told you guys a story about me putting up a fence. I gave up after 3 posts. So I hired a guy. He's like, yeah, I could do fences. He showed up and asked me to borrow a screw gun. And at the time, I didn't even know what a screw gun was. But I had an electric drill. I had what he wanted. I didn't know it was called a screw gun. So, yeah, he could put up a fence, but he didn't really, have the tools to do it, so on and so forth. Hire the right person for the job. Anywho, so water table, usually it's an upside-down triangle on a line. They show that on maps sometimes. That marks the top of the unsaturated zone, is how we tend to think of it. You don't want to say the bottom of the unsaturated zone. You want to say the top of the saturated zone. Capillary fringe just means, again, there's going to be a little bit of water above it. We tend not to worry about that, though. So all of this water that we've been talking about is to fill up an aquifer. An aquifer is a body of rock or sediment that yields significant amounts of water. Yields, gives off. The way we measure that is 2 words, porosity and permeability. Porosity, or holosity as we like to say sometimes, is the amount of pore space in that rock. Most folks have a sponge sitting on their counter at their kitchen sink. Think of that sponge. And as you're thinking of that sponge, picturing that sponge, you could argue that that sponge is 60% spongy material and 40% holes, let's just say. I've never actually measured a sponge, but I think that's a good guesstimate. 75-25 is probably a bit much. I don't know. It could be close, though. Doesn't matter. The amount of holes in that sponge is porosity. So again, if we just said it is 60% spongy material, 40% holes, that sponge would have a porosity of 40%. Now, when we actually move to numbers for rocks, you hardly ever see a porosity that high. Okay, but I'm just, again, giving you an example. Now, permeability is something different. Permeability is how connected are those pores. I like to call permeability flow-through ability, because we want to know if those pores are connected, how well can that water actually move through it? And you're thinking, well, wait a minute, how can you have all those holes and not be connected? I might remind you of Swiss cheese. Excuse me. So, picture a nice big old wedge of Swiss cheese in your hand. And again, you could argue that that Swiss cheese, well, maybe not 60-40, is at least 50-50, okay? Cheese to holes. Put that hunk of cheese underneath your sink and turn on the water. What's going to happen? Water's going to splash everywhere. It's going to hit those top layer holes, fill up, and just go run everywhere. Those holes aren't connected. They're there, but they're not connected. And this brings up a whole other point of how you can achieve porosity. Several large holes, many small holes. You could still end up at the same porosity, but you get different permeabilities. It's actually, again, an entire semester class talking about groundwater. We're doing it in 28 minutes, if not less, 18 minutes. So, not only having good porosity is important, but having good permeability is just as important. You put both of those together, you get yourself a good rock for a good aquifer. As I said, a good aquifer tends to be sedimentary rock. Now, it won't take you long in life if you're talking to someone about wells, which you might tend to do as you get older. Older people talk about stranger things. And you're going to run into someone who brags about their granite aquifer. Usually they're going to be from Vermont, New Hampshire, thereabouts. They're not lying. They have a granite aquifer. And they're also not lying. They don't have hard water. They don't have iron in their water. They don't have anything in their water because you're not going to dissolve anything out of granite. They may have a lot of pollution in their water because sedimentary rocks, in addition to water flowing through, also act as a filter. What's one of the best pool filters they got out there? Sand filter. Okay? That water flows through there. It catches all kinds of stuff. In the granite aquifers, or any igneous rock aquifer, their water is in giant cracks. The earth is old. She's cracked. It happens. We get it. And water does pull up in those. They know where those cracks are. They can figure it out. They tap into it. You've basically got an underground reservoir. Okay? The only problem is, as I said, if there's an old septic nearby, an old sheep farm nearby, an old whatever, that all goes down in there as well. You've got to filter that stuff. But otherwise, it's fresh and crisp and clean. So, anywho, we got two other words that are going to show up in your textbook, because I know you guys all read these chapters. We got aquatards and aquacludes. Now, I argue that if an aquifer is a body of rock or sediment that yields significant amounts of water, enough that we can drill into them, blah, 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 why we would say there are two other kinds of aquifers that basically suck. But we do. So an aquatard, what does to retard mean? Okay, timing, well, yeah, usually to slow something down. Okay, to retard something is to slow it down. So an aquatard has a slow flow. Which of those terms, porosity or permeability, would give us this slow flow most directly? Is it the amount of holes or the way stuff can flow through the holes? Yeah. No, the flowing through the holes. Porosity, most directly. Porosity is related, but most directly, we're going to say that it has a pretty low permeability. Okay, the holes aren't connected real great. Okay, aquaclude, on the other hand, is an exclude. Again, why are we even calling this an aquifer? I don't know. An aquaclude, you're not getting any water out of it. Now, the reason, I know why they fit in, but to you guys this sounds like, okay, you just told us it was this, now you're giving us two examples that aren't that. Shale. Silts and clays love water. They're like sponges for water, okay? So much so that they hate to give it back. You got a layer of shale and you're looking at your aquifer, it's essentially like Tupperware, okay? And in fact, when we go to the point of looking at diagrams and drawing these things, we want to put an impermeable membrane in there, we want to put a bottom to our aquifer, or we want to put a top on it for some other strange reason. We use shale. It may as well be granite, okay? It's a great boundary layer. It's impermeable. So, aquifer, good porosity, good permeability, sedimentary rocks. Aquitard, you got the holes, but they're not connected real well, poor permeability. Aquaclude, again, you probably got the holes, and you got either no permeability, or you're looking at shale, or you got no holes at all. All right. Perched water table, sometimes called a false water table. We got a lens of shale. We use the word lens there. It kind of looks like a contact lens, that little black. Remember, shale is those dashed lines. What were the dotted line, or not the dotted line? Yeah, the dots. They're not lines though. So the dashed lines was shale. They made it black to help you remember in this case. The dots were, remember rock cycle diagram, is sandstone. Yeah, it's sandstone. So we got a nice sandstone hill here with some bits of shale here and there, and that shale is doing, guess what? It is catching water. And this is that example of you hire the cheap well driller. Okay, he's like, I've got water for 100 feet now. You're good. You're good. In this first perched water table here, it turns out you are nowhere near the water table. Okay, that little lens of shale is going to dry out super quick, and you'll be without water. Can't emphasize enough. Go to the town hall, find out the average depths of the wells around you, so on and so forth. These are kind of cool. If you drive down 90, again, especially in the wintertime, you see those amazing ice flows off the sides and the cliffs around little falls and whatnot. All right. What's happening is the water is hitting these shale layers, and that's all shale, but it's fractured, and so it flows pretty good. But it's going to hit a solid layer. And again, once that fills up with water, it becomes Tupperware. Nothing's getting through it. It runs off in the slope, whatever direction it's sloped. On 90, it's sloped towards the road, so you get these cool ice flows. And they're so cool and blue in the wintertime. In the spring, $5 bet, okay, you're going to walk along and you're going to see these little waterfalls here and there coming out of the middle of these layers. It's hitting one of those shale layers. We call that a spring when the groundwater leaks out at the surface. We told you that we call everything a stream no matter what, size, da-da-da-da-da-da. Spring is the exception to that rule. A spring is groundwater leaking out at the surface, okay? Super important you remember that one. When they say fresh spring water, it darn well better be leaky groundwater. A spring is not another name for a river or a stream. All right, probably one of the last things we're going to talk about here. Artesian well versus a pump well. Okay, and we don't have bucket wells anymore, but a bucket well is essentially what's nowadays is a pump well. You got to do something to get the water out. Those of you that may have well water, you probably got a pump somewhere in your basement, outside, upstate New York. Probably not best to put a pump outside, but some might still do it. So an artesian well is different because it is self-flowing. It is self-flowing because it is pressurized. We told you that shale is impermeable, right? So what we have here is shale on the bottom and shale on the top. We're sort of skipping our conversation about confined and unconfined aquifers, I see. All right, so that's fine. Remember, like I said, I have my stories that I tell, and sometimes my slides don't match them. This is one of them. So this is a special kind of aquifer that has a lid on it. It's got shale up top. Because of that, and the fact that it's on a slope, it's pressurized. And there's a handful of uncomfortable conversations in geology. This is one of them, because they call this head when it has pressure like this. And they're going to say things like, it has good head, it has bad head, and all kind of variations on that, and everybody giggles. Even the 50-year-old geologists giggle. But it's all about head. So, what we have is head 1 to head 2 here. We've got the top of the aquifer to the bottom of the aquifer, or at least where your well is. And the difference there is what's going to give us our water pressure. All right. This is why water towers. Used to think it was so people wouldn't put, stuff in the water, teenagers wouldn't pee in it, whatever, dump beer in it. It's not. It's for water pressure. So you can do this at home. You can show this, prove this yourself with a very simple experiment. What you need is a length of plastic tubing, a funnel, and some sort of liquid. All right? And a helper would be good. So what you're going to want to do is you're going to want to put this in both hands. You're going to have the funnel on one side, the end of the tube on the other side, and you're going to want to put your thumb over the tube. All right? Now, you hold up your hand and you have your partner pour some liquid into the funnel and let it fill up very slowly all the way through the tube. And you might want to let your thumb off a little bit to let it breathe through there. Okay? Get it all filled up. Now, hold that up nice and high. Take your thumb off. What happens? No? No? Water comes right out, or whatever liquid you have in there comes right out. Okay? You guys have the advantage these days of having slow motion cameras right in your pocket. Back in the day, we couldn't prove this. What you should be able to see, and you could win a $1 bet here. I wouldn't bet too much because it's hard to catch, even with a slow motion camera. When you take your thumb off of there, the water should shoot up as high as the funnel. It should. That's what they're showing here by the red line. That's that head equaling out. Now, this one I would place a $5 bet on. You did that, emptied it out, fill it up again. Now, bet someone that you could take your thumb off of the end and nothing will come out. How do you do that? Well, I don't know what you're doing with your hands there. Same height. What's at the same height?
The level of the water to the end of the hose.
And what are you doing by doing that? You're removing the pressure differential. You're removing head. Exactly. All right. So you say $5 says I'm gonna take my thumb off of here and not spill anything. You're on. Especially if you guys have done this a couple times, you'll be more willing to take your bet. You lower the funnel, take your thumb off. You're good. You've removed pressure from the situation. Artesian well is a self-flowing well. It's really cool. This is like when you see in the old movies, they pop a hole in the ground and the oil shoots up and everyone's dancing around. Yay, 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 yay. Same thing but with water. You got to cap these suckers off or they'll run dry. On the other hand, there's the confined versus unconfined. On the other hand, you got your pump well. Your pump well is essentially, as we said, that lowering of the water. You got to go down and get it yourself. We don't have buckets anymore, okay? We've got pumps, typically electric. You got to have backups on them when the power goes out, or you're not going to have any water. These are great. They're easier to refill, to recharge, because you don't have that lid on them. The water trickles down from the grass, and it goes right into your aquifer. You're good to go. I need a couple more minutes, and you guys will be good to go. So, the only problem with these is that cone of depression there. You guys have all had a cone of depression in your Slurpee or your Icy or your Slushy, whatever you happen to call it. You got your straw in there, and you're sucking away, you get the brain freeze, you stop for a minute, you drink a little more, and then all of a sudden you start just kind of sucking air, and you're like, I can feel it in here. There's more slushy in here. why aren't I getting? You look down and you cleared out that area around the straw, right? You got to shake it up a little bit, poke it around, and you now got a full drink again. Just like that, this pipe is going to clear out the area around itself first. If, the developer, whoever decided to put in where these houses are where you are, they should have checked for stuff like this, that the average use, so on and so forth. You should be able to use your sink, use your toilets, do a load of laundry, and that water will flow back into place as quickly as you use it. Again, you are flowing through rock. Think about that. Okay, it's hard to do. But it works just fine if we do the math right. But sometimes it still happens. We lived on a place, it was an old farmhouse split into like 3 or 4 apartments, and there were a couple trailers, mobile homes, whatever they call them, out on the property as well. And again, we all got along fine, except on the holidays. You got more people over, more toilets flushing, more dishes being washed, more this, more that, and occasionally we would suck some air. But otherwise, the flow rate matched the thing. So just to go back one slide, all right, confined versus unconfined aquifer, that's what we've been talking about. Confined aquifer has that top stone on it, that top membrane or impermeable layer. Because of that, it's pressurized, it's self-flowing. The unconfined aquifer is unpressurized, you don't have that capstone. Even if it's on a hill, you're still not going to get the head you would otherwise. All right? And that we need the pump well. All right. I do think that is where we're going to stop. So wells, pump well, unconfined, cone of depression, artesian well, confined aquifer, head. All right, we talked about all of that. So that is 2 chapters blended together, okay? I do want you to review this stuff. In this case, use the PowerPoint as your guide, which I will post during my office hours in a little bit.